All right, I'm going to get started. So today we're having a quiz on sections 2.3 and 2.4. So I figured I'd kind of just review that a little bit before asking if there's any questions about section 2.5 homework. So for lines, I mean, everything boils down to this. You want to write out the equation of a line in this form. Right, this is slope-intercept form. All right, m's the slope and b is going to be the y-coordinate of the y-intercept. All right, so that's the goal. You want to get it in that form. So you're given a bunch of information, and really the equation you use is this equation. All right, this is point-slope form. So I don't want you to get these confused. All right, so this is slope-intercept. Oops, my point spell. And this is point slope. All right. So for point slope form of an equation, you essentially need a point and the slope. So you can do this a couple ways. I could just give you some slope value. Let's say m equals 2 and the point 1, 3. All right. So when you're going to use point slope form with this information, I see mistakes a lot like this. So this point 1, 3, in terms of the variables in that equation, is x0 and y0. You want to end up having y and x in the final equation of the line, right? Because that's the same y and x that are in this equation. So if I have that slope 2 and I have x0 and y0 as 1, 3, you just plug in the values. So we have y minus 3 equals the slope is 2, and you get x minus 1. All right, so the y and x are always going to stay there. So now all you have to do is get that equation, this one here, into slope-intercept form. So you distribute the 2 here, so you have 2x minus 2. The only thing to be careful of is here and here when you plug in x0 and y0, if your coordinates are negative, right, so if that one was negative for x0, it'd be y minus a minus 1, so you end up getting a plus, if that makes sense. Okay? So now you have this, and then you basically just solve that equation for y. And let's see what we'll get. We'll get y equals 2x plus 1. So clearly that's in slope-intercept form. So a couple different things I could give you is, if I don't give you a slope and a point, but what if, so that's one way. Another way is, what if I gave you 2 points? What would you do first if I gave you 2 points? Yeah. You'd find the slope, right? So here's our equation for slope. It's rise over run. So it's y2 minus y1 over x2 minus x1. And again, if you have to label the points, that's fine. So I'm going to say 5 is my y2. So 5 minus a negative 1, right? I just did that to the y coordinate. And then x2 minus x1 will be, again, I have to start with the 2 here, so negative 2 minus 3. So we get 6 over negative 5. So that's my slope, negative 6/5. Now that I have that slope, I can pick any of those 2 points, or any of those 2 coordinates to use in point slope form. I won't go through that exercise because I clearly just showed you how to do that. So if I gave you 2 points, find the slope and then do the same thing that I just did above. Now there's a couple cases. For example, if I gave you, let's say, 2 comma 0, and I said the slope is undefined, what's the equation of that line? So I'll actually go all the way back up to the top here. Right? So there's a bunch of cases for lines. You could have lines with positive slope, lines with negative slope. You could have horizontal lines and then vertical lines. So a vertical line has a slope that's undefined, so it only ever has an x coordinate. So if you see slope undefined, all you have to do is say x equals whatever the x coordinate is in the point. So this would be x equals 2. So that would be the equation of a vertical line at the x coordinate of 2. Okay? The only other case would be, let's say I gave you 5, negative 4, and I said, well, the slope is 0. A slope of 0 is a horizontal line. So that means, and really, for this one, you could still plug it into this equation, right? Because you'd have y minus a negative 4 equals 0 times x minus 5. So you see, this whole term's going to be 0. So you'll have y plus 4 equals 0, so y equals negative 4. So horizontal line, you just have y equals whatever that number is, because it only has a y coordinate. And then undefined or vertical lines are x equals 2. Okay? Now, the only other part, I believe, of this section was, okay, if you had parallel lines, right? What's the relationship between two parallel lines? They have something in common. The slopes, right? So like if you have, and I won't do an example, but if I give you an equation for a line, if you found the slope of it, and then I gave you a point, let's say, 1, 3, and you'd have to figure out what M1 was, and that's going to be the same thing over here, because they're the same slope. For perpendicular, having a tough spelling bit. Must be the rain. What's the relationship for perpendicular? It's the opposite, it's the reciprocal, and it's the negative of the reciprocal. So like if you're looking for M2, like the slope of a line that's perpendicular to another one, you take the first slope of the line and do 1 over that, and then just tack on a negative sign. So let's say M1 was 1/2. Okay, so what's the slope of a line perpendicular to this one? You would just put, right? So 1 divided by 1/2 just gives you 2, but that you're also negative. So the perpendicular line would have a slope of negative 2. Okay. But everything boils down really to writing out a final answer in slope-intercept form. Now, I give you 2 equations. I give you this equation on the quiz. Slope-intercept, I don't give it to you, because I think that one is probably etched in everyone's brain. But just in case, I also give you this equation for slope. Okay? They're the 2 that are on there. I can't think of anything else from section 2.3 that we did. Does anyone have, is everyone okay graphing the line? Okay, what you could do is, if you're in slope-intercept form, B is the y-intercept, so let's just take this as an example. The 1 here is B, so that means you have a point 0, 1. Right? That's the y-intercept. And then to get a second point, I think the simplest thing would be to plug 0 in for y. So if I plugged in 0 in for y, I'd have 2x plus 1. So I'd eventually get negative 1/2. So that's the x-intercept. Right? Plot those 2 points on a graph and then just connect them with a straight line. That's the simplest way to plot. You could use the slope, but that's, I don't know, I think this is a little easier if your final answer is in slope-intercept form. Other than that, any other questions on section 2.3? All right, cool. I hope lines are fairly easy. So let's look at 2.4. So 2.4, this was the functions section, just introducing to you how they work. So let me just kind of go through. So if you have an equation for a line, like y equals 5x minus 2, that's in slope-intercept form. To make this a function, instead of having y there, we just put this f of x. All right, so this is just symbolizing essentially y. All right, so when we plot something, f of x is in the y direction, right? It's really this, you could think about it the same way, and then horizontal is x. So in order to get coordinates to plot this, you would plug in x value. So I chose x equals 4, so I plugged in 4 to the function. Now, that's the input. When you evaluate the right-hand side of the equation by plugging in 4, so in this case you'd get 18, that's the output. So the output of the function is the y coordinate. So if you have f of 4 equals 18, 4 is the x, and 18 is the y. All right? So you could plug a bunch of numbers in for x and get a bunch of y values, just like we did when we made a table, and then we graphed the equation using the table. It's the same thing. Now, we already talked about the domain in several sections prior to this, but we just kind of defined it as it's the set of numbers that when you plug those numbers into the function as inputs, so like for the x value, you get a real output, okay? So, for example, if you plugged in an x value that gave you an imaginary number, that's not a part of the domain. If you plug in an x value that makes the function undefined, that's not a part of the domain. And they were the two main things that we focused on, okay? For lines, since lines go everywhere in the x and everywhere in the y, their domain and range are the same, negative infinity to positive infinity. Now range is just the set of all the outputs that are real. So I gave you a couple examples. So like this one here is a square root. As soon as you see square root, you should start thinking, okay, imaginary numbers I have to worry about. So I gave you an example. If I plugged in -4 here, I'd get the square root of -1. That means -4 is not a part of the domain of this function. So you remember this process from a previous section. We take the radicand, this thing, that has to be greater than or equal to 0. So then we get the inequality x is greater than or equal to -3. And when we do domain and range now, we have to do it in interval notation. So hopefully x is greater than or equal to -3. That looks like that here, right? We're going to have a square bracket because it's greater than or equal to 3. If it was just greater than -3, we would use a parenthesis. Now the range, the only way we know how to do that as of right now is to look at a graph. So the range, you're looking in the vertical direction, and what you want to do is you want to find the smallest possible value, all right, that exists on the graph in the y direction. Now for a line, if you see an arrow like this, that's going all the way down to negative infinity. That's why the range started at negative infinity here. But when we look at the square root, the lowest value I get to is right here. And that has a y value of 0. And then you see it has an arrow going upwards, which is signifying it's going to positive infinity in the y. So there's the range. A bracket on the 0 because 0 exists on the graph as the lowest point in the y direction, and then it goes to positive infinity. And then we just went through a bunch of examples. So everyone understands what an open circle is versus a solid circle. Again, finding the domain and range of these are pretty easy. And then the only other, I think this is it, right? All we had to do then, instead of looking at a graph, I gave you equations, which were really functions, right? Here, instead of having y equals something, we have y of x, h of x, and all these function definitions on the left. And you just have to figure out the domain, right? Because without looking at the graph right now, it's too difficult to calculate the range. So we just went through a couple examples. Again, look out for the square roots, and then look out for something like this, where you have a rational expression, right? It's the fancy term for a fraction that are polynomials. What you're looking for is what values of x in the denominator make it undefined. So you have to, this one you factor it, and you see that x cannot be equal to plus or minus 3. So for the domain, it's everything but those numbers. So that's what this looks like here. Right, you go from negative infinity to -3, and we have a parenthesis because we do not include -3, and then we union it with these other intervals. I hope that makes sense what you see there. Right, that's basically just saying we're ignoring -3 and 3, and it's not in the domain. And that was all section 2.4. Are there any questions about 2.4? Yes, sir. So if you plug in a number in a square root and you get undefined, you just don't have a coordinate at that x coordinate. No. I mean, if you get i's and stuff, you can't plot that, right? I mean, there's a way to plot complex numbers, but that's not what we're doing. So if you plug in a number, right, when you're trying to make a graph, just ignore those x values. You know, the easiest thing is in a square root, try to figure out the number to plug in that makes that square root 0, because that's the first point. And then all the other points after that are easier to find, if that makes sense. Okay? Anything else in 2.4? All right, so that's the review for the quiz. Hold on, some people have popped in. I just want to make sure I get you down here. Okie doke. All right, so that's the quiz material. So I gave you a homework assignment in 2.5. 2.5 was properties of functions. We did even and odd functions. That's basically testing for y-axis symmetry and origin symmetry. So that really wasn't anything new. We just had different definitions for functions rather than equations. And then the big part of this was finding intervals of increasing slope values and then intervals of decreasing slope values. And we had to identify things like turning points and relative mins and maxes. Hopefully that's fairly simple. This is another example here. And then we went into average rate of change, which is sort of a segue into stuff that you'll eventually learn in a calculus course if you ever take it, or in economics and other business courses. And then we ended up using that average rate of change to look at something called the difference quotient, which was important in determining a functional representation of all of the slopes of a function. So if you have like f of x equals x squared plus 2, okay, that's a parabola, okay. There's a function that represents the slope at any location on that parabola. And that's essentially what you use this difference quotient for. So there you go. There were the homework problems. There weren't that many. Are there any questions on any of these 2.5 homework problems? Okie doke. Perfect. All right, so we had briefly started section 2.6. And I think 2.6, I think it's called a library of functions, okay? We're going to talk more about different types of functions in the next section, but I only really wanted to cover two types of functions that you need to know coming out of section 2.6. All right, so the first one is one we've been working with. We worked with it all in 2.4 and then all in 2.3. It was a linear function, okay? And it's essentially how to write out the equation. So this is actually a good review on functions. So let's just do another example. Let's say I gave you f of 2 is negative 4 and f of 5 is 10. Okay. So what does this mean? Okay, well, this is going to allow you to get 2 points. Okay? The points are going to be 2 comma negative 4, right? Because this is the x value, and then this thing, negative 4, is the output to the function, which is the y value. And then we could do the same thing for f5 of 10. All right, now it becomes a section 2.3 problem. I got 2 points. I want to write out the equation of a linear function. So it's the same step as 2.3, so you're getting some extra review here. First thing we need to do is do the slope. So I'm going to call this x1, y1, and then x2, y2, right, just in case you need to label them. So we're going to do y2 minus y1, so 10 minus a negative 4. And then x2 minus x1 is 5 minus 3. Okay, so we have m over, what do we have here? That's 14 over 2. Oh, look at that. So we get a 7. Wonderful. All right, now I have the slope. Now we want to use point slope form. Let's say you could choose any point. I don't know which one to be better. I'm going to do this first one here because it's got a negative number. So it's going to be y minus negative 4 equals 7 times x minus 2. You go through the process of solving for y. So you have y plus 4 is 7x minus 14. So y equals 7x minus 18. All right? The last step to make this a function is just to change y to f of x. That's literally it. So you sort of have to remember this stuff here from section 2.4, how to get points from functional inputs and outputs. Go through the section 2.3 line process of getting slope-intercept forms, and then just replace y with f of x. It's really that simple. All right? And again, if the book problems ever said, well, what's the domain and range of a line, what would you say? Wouldn't it both be like the D and the R? Would both be negative infinity to positive infinity for a line. They're both the same. All right, so that's one type. I don't think you need another one of those because there's two here already, and the book has a bunch. They're pretty simple. Okay, the next function. You've probably seen it at some point, but maybe you haven't. It's actually used extensively in a lot of the business classes that you're going to do, because a lot of times, let's give you an example here. So if you have this coordinate plane here, you might have, I don't know, revenue, right? That's how much money the business is bringing in. Now the x-axis might be time, right? And let's say, that time is in years, right? It could be that, your revenue goes like that over time, like a parabola. So it is a function. But it might not. It might, at the beginning of your business maybe it's linear, right? And then COVID hits, and then you don't make anything, right? And then it increases again, and then it goes up like a curve, all right? So you have a bunch of different looking things, right? But you can't write it out in one line, okay? There's pieces to what your revenue looks like over time. Does that make sense? Okay? So this type of function where you have multiple functions within the same function are called piecewise functions. Okay? So I'm going to write this as my bad econ example. Actually, that is pretty reasonable like that. All right, so let me just give you what it looks like, all right? Because you're going to have multiple functions. Now, the one I drew over here, it looks like it has 1, 2, 3, 4 different pieces, okay? I'm probably not going to give you a 4-piece one, so let's just start with a 2-piecewise function. You could still call this f of x, but then after the equal sign, we just use a big bracket, and we just have two different function definitions. But this is how it'll go. Let's say this first one is 2x, right? So when you define the first piece of a piecewise function, you have to indicate after the function what the interval is in which this function exists. So I'm going to make this one real simple and say this function f of x is 2x when x is less than 0. And then say f of x is x when x is greater than equal to 0. Okay? All right, so what do we get? So that's what it looks like. And however many rows you have after that curly brace is how many pieces you have to the function. All right, so they're going to want you to graph these things. All right, so I'm going to try to draw this nicely. So we're going to need f of x on the vertical or y-axis, and then, x is still here. So we're going to have two pieces to do here. All right, so if you have to put it off to the side, you can. Let's start with, I usually just start with the top row, do that first piece. So it's 2x. So we need to get a couple points. So again, if you have to write this over here, like f of x equals 2x, right? That's the same as saying y equals 2x. So what's the y-intercept of y equals 2x? Right, if you wanted the y-intercept, you'd plug in x equals 0, right? So you'd have y equals 2 times 0. Oh, so look at that, so y equals 0. So that means the y-intercept is at the origin. But what you want to be careful of, see how it says x is less than 0? That means the 2x exists only when x is less than 0. So what I'm going to do is, just for the moment, because I don't know anything about the next piece yet, we didn't analyze it yet, I'm going to go ahead and put an open circle at the origin. Does it make sense why I'm doing that right now? Putting that open circle, because for 2x, it only exists when x is less than 0. So I can't even say that 2x is going to be there, all right? Because it might change once I look at the next piece, but for right now, I'm going to put an open circle. Now what does 2x look like? Well, the slope is 2, so that means you're going to go up 2 and then to the right 1, right? Rise over 1. Well, you can go backwards and say left 1 and down 2. So I have a point right here that's on 2x, and I'm just going to connect these lines. Okay, so there's the piece of this function that's 2x, and where x is less than 0. So if you have to off to the side, figure out 2 points for that, that's fine. Or if you know automatically, well, yeah, that's at the origin, then you're good. Okay, so I'm done with the first piece. All right, the next thing to do is the second piece, the last piece. So it's just f of x equals x. That's easy. We also have, if we plugged in 0, we get 0. So that means the y-intercept and the x-intercept are, again, both at the origin. But since this one's x is greater than or equal to 0, and I might actually change colors just so you can see what's going on here. That means this origin point, 0, 0, because we have x is greater than or equal to 0, this does exist here. All right, now you just have to graph x, which is easy. Like if you plugged in f of 1, you'd get 1. So there's a coordinate 1, 1 that exists. And then we just connect. So there you go. So it's basically just 2 lines, different slopes, and they change at the origin. Okay. Any questions on that one? So we really do have that point 0, 0. It's just not a part of the first piece, but in the overall function it exists. Okay? Good with that? Yeah? All right, let's do another one. Which one's next? Yeah, let me give you I'm going to give you a 3-piecer. We'll call this g of x with a big curly brace. Here it is. Let's see. This is a good one. Negative 2x when x is less than negative 2. 3 when you're between 0 is less than x is less than or equal to 2. And then just x when x is greater than 2. Oh, by the way, they're probably going to ask for the domain and range. Going back to this first problem piecewise, what's the domain and range here? Are all the x values give you a real number? Yeah, so again, it's negative infinity to positive infinity for both of these. Okay, I'll let you know this one's not going to be that way. Okay, so let me draw up this axis. All right, we have x here, and we have g of x. All right, again, let's start top down. We're going to look at negative 2x when x is less than 2. All right, so when you're looking at those intervals, that number is important because if I take, let's just say, g of x equals negative 2x when x is less than negative 2, I have to figure out the coordinate when x is negative 2. All right, so when I do that, I get g of negative 2, and I get negative 2 times negative 2, and negative 2 times, what am I doing? Negative 2 times 2 is a positive 4, right? So I can do that simple math. So here's my coordinate, negative 2, 4. So I know I need to put something there. So let's see, negative 2, 1, 2, 3, 4. All right, so what's going to go there, though? Is it going to be a solid circle or an open circle? And how do you know? Yeah, Tom. It's open because right here is a less than sign. If you wanted a solid circle, that would have to be a less than or equal to, okay? So here's what I'm going to do. I'm going to put an open circle there. All right, so what do we do from here? Well, we have to find at least one other point. So since we're less than -2, you have to pick a number that's less than -2. So I might pick -3, right? That's less than -2, and see what we get. So -2 times -3, we get a +6. So another point on a line that's -2x is going to be -3, 6. Okay. -3, and then we'll go up to 6. All right, so that's an actual point. And then all you have to do is connect. Remember, 2 points gives you a line. And we know it's going to go like this. All right, so that has a negative slope. All right, piece 1 complete. These are kind of like, I don't know, they feel like puzzles to me. But again, here I am teaching it, and of course I kind of like it, so there you go. All right, next one. Yes, sir. Oh, okay. So it's -2x when x is less than -2. So any x value lower than 2 is on the function. All right? So when you're getting that second point, right, sometimes we call these points, like when I plugged in -2, the number that was in the interval, that's like a critical point. Something's happening there. Either we have it or we don't have it. But anything, any x value that exists in that interval, like -3, -10, -100, they're all going to be there. Okay? All right, next one. Look at this interval for g of x equals 3. It's 0, less than x, less than or equal to 2. Okay, so we have to figure out, because there's 2 numbers in the interval, we have to figure out 2 coordinates by just plugging them into the function. So this is kind of silly for this one, because if I did g of 0, I still get 3. And if I get g of 2, I still get 2, right? Okay? Oh, I'm sorry. I'm still going to get 3. Right? When you have a 3, that means it's constant, which means it's going to be a horizontal line. But I have to figure out, do I have open circles, closed circles, or whatever. So what about at 0? Is that an open circle or a closed circle? Right, so this point is 0, 3, and this point is 2, 3. At 0, 3, do I have a solid or open circle? You raise your hand? Oh, I'm sorry. Yeah. It's open, right? Because look, where the hell is it? I can't find it. Oh, right here. Less than. That means open circle. So we're at 0, 3, and it's open. All right, at 2, 3. 1, 2. We already have the y there. Is that solid or open? All you got to do is look right here. Yeah, that's a solid right here. And then everything between is you just connect the line. And then let's get one last color here. The last piece is g of x when x is greater than 2. Again, this critical point 2 is important because I need to figure out what's going on here. So I'm going to do g of 2 equals 2. All right. So I get a point 2, 2. So tell me, is there a solid circle or an open circle at 2, 2? Anybody? It's open, right? So at 2, 2, which is right here, open. And we really just need to figure out another point to draw the line, because we know g of x equals x is a line. Now this is nice, because if I do g of 3, I get 3. So there's a point 3, comma 3. So if I put that in, there's that point, and then I just connect, and there you go. Well, look at that freaky thing, right? 3-piece piecewise function. Now, domain, range, and interval notation. Anyone want to take a stab? Go ahead, yeah. Yeah, sure. It's greater than, yeah. So any number greater, any number that exists in that interval, I could have chose 10. I just didn't want to draw out 10. You know what I mean? All right, who wants to give the domain? So this is all the x values that have a color on this graph. Doesn't matter what color, because the domain is for the entire function, not for each piece. So start on the left. Where do we start all the way on the left here? Go ahead, yeah. Okay, and do we have a bracket or a, nope, we've got a parenthesis, right, because of the open circle. We're going to union that with something. Parenthesis. Okay. And what did you say the next one was? Okay. That's because you see this dot right here, right? But, so if I plugged in x equals 2, I get 3, right? And then any other number I plug in after x equals 2, I have a value all the way to positive infinity, right? So that's a tricky one. When you have either a circle above a dot or a dot above a circle, that means that point's included in the domain. So this one, I could just say 0 to positive infinity. We're really only excluding the numbers between 2 and 0, including 2 and 0. Okay? All right, now these are tricky, but we'll have more examples. What about the range? Again, we're looking vertically. What's the lowest value of y that exists on this graph? Or actually, what you can think about is what's the lowest dot or open circle? And what y value is that located? Come on, what's the, yeah, go for it. It's 2 right here. Isn't this that's the lowest critical point, the lowest open circle. Okay, so that's what we're going to start at. We're going to start at 2. And is it a bracket or a parenthesis? It's a parenthesis, right? Because it doesn't exist, right? So it's everything from 2. And do we have to exclude anything? Or does it go right to positive infinity? Just, I mean, if you look at right here, you see that all these values exist? So you go right to positive infinity. So every number above 2, excluding 2, exists as a output to this function. Even though there's circles here, right? There's a circle here, but who cares? We have a point actually clearly right there. Who cares about this circle? Because we have a point right here that's at the same y value. So it doesn't matter that those open circles exist, as long as there's a corresponding point on a function that's there or another dot. All right, I'm going to do one more, and then we'll do this quiz. I'm going to take one from the book. I was going to start the next section, but I will wait to do that on, let's say, Thursday on Tuesday. So I'm looking, what am I? Section 2.6? Let's find a nice one. How about, I'll just do a tour. Yeah, let's just do this. So this is number 24 out of the end of section 2.6. We have g of x equals just a 2-piece actually I modified it a little bit just to make it a little more fun. All right, 2-piecer, here we go. So we got g of x, and we have x. All right, so let's start with the first piece. G of x is 3 times, and everyone's okay with this symbol, absolute value, right? It's easy. Whatever number's in there, even if it's negative, you just get the number. So this is when x is less than 1. So clearly 1 is a critical number, so I have to plug in g of 1. This is why we spent that time at the beginning of the section 2.4, because You really have to understand that if you have an x value and you plug it in a function, and then evaluate the function, you're essentially getting the y coordinate. So here's a coordinate, 1, comma 3. So I got to put that in here. Okay, open circle, closed circle. We're less than 1. So if I'm just looking at this piece, it should be, for now, an open circle. Okay? I mean, when we look at the second piece, it may not end up being that way, but if I'm just looking at that first one, I'm going to, for right now, put an open circle. All right, so this is a interesting one because it's an absolute value. So here's what I'm going to do. I'm going to plug in g, so something less than 1. I'm going to plug in negative 1. Okay, that's less than positive 1. So 3 times the absolute value of this is just 3, right? Because absolute value of negative 1 is positive 1. So I have negative 1, 3. Okay. Let's see. Negative 1, 3. Did I screw something up? Let's try another one. I'm going to do negative 2. We'll have 3 times the absolute value of negative 2. So that gets me 6. So that's negative 2, 6. That's interesting. What if I plugged in 0? Oh, yeah, this one's tricky. If you plug in g of 0, you get 3 times 0 is 3. Or you get 0. So that means the origin's 0. So, okay, before, we haven't really done one of these before. If you look at the regular graph, I probably shouldn't have chose this one because I don't know that we've covered it yet. If you had f of x is equal to absolute value of x, it looks like this, right? It looks like a line, like you normally would here. So, like, if this was just f of x equals x, you would see that it would go down here. But that's not what the absolute value is. It basically just flips that and it looks like this. So that's why, since I'm starting on the right side, essentially what this is going to do, it's going to go down to 0 and then go up this way. That's why I was like, what the heck? Because I knew it was going to look like a line. But so this is kind of interesting looking. All right, so that's the first piece. Sorry for that brain fart on my account. All right, now the next one, we know what this is going to look like. G of x is equal to x squared minus 1. Okay, when x is greater than or equal to 1. So again, critical point is 1. So g of 1 is 1 squared minus 1. Well, how about that? That's 0. So we have a point 1, 0. Now, is that solid or circle? Look right there. Solid. Okay. So that was good I didn't fill in that circle to begin with, because this one's interesting. 1, 0, it starts right here. And then, what is x squared? That's a parabola. So let's get a couple points. Let's do g of 2. It'll be 2 squared minus 1, which is 4 minus 1, or 3. So we have a point 2, 3. Here. And then we'll just do 4. 4 squared. No, let's do 3. I don't want to get too big here. 3 squared minus 1, that's 9 minus 1, or 8. So we have 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 3, 8. And then this one's kind of curvy, right? Because it goes up like that. All right, so that's a very interesting looking piecewise function. All right, last step before we do our quiz here. Domain. Range. How about the domain in this one? Are there any x values where the function doesn't exist? Clearly we come like right here, right? That's coming from negative infinity, so I know I'm starting there. Is there a problem at x equals 1 or no? Like if I plugged in x equals 1 into this function, do I get a number? Yeah, I get 0, right? So that means the domain is negative infinity to positive infinity, because every x value can be plugged in to this equation. How about the range? What's the lowest value we have? Just look vertically. And is it a bracket or a parenthesis? Bracket 0. And it looks like we go all the way to positive infinity. Boom. There you go. Beautiful. Okay. Homework. Section 2.6. What am I doing here? 259 to 260. I have 9 to 15, and then 19, 21, 23, 25. Those last four you're going to be graphing piecewise functions, so that's why there's so little problems. And actually 9 to 15 is also odd. Okay? Okay, so this will be homework number 3. Okay, for the last exam. The Dropbox is already out there. Do you guys like having 2 sections, because then you get +4? Because, like, if everyone's doing the homework, that's 12 points added to your exam. So I feel like we'll just do it, right? All right, so you're going to hand in, so you're going to submit sections 2.5, which, you know, theoretically, I assigned it Tuesday, it should be done already, and then 2.6. And then this will be a +4 homework. I think that's pretty reasonable. Okay, so we are going to...